Welcome everybody to 52 Living Ideas. This is the Bucky inspired Comprehensivity for Understanding and Changing the World series. And I am delighted to finally have Kirby here. And he's going to be taking us on a deep dive into synergetics. The format is we're going to start slow. We're going to talk about the general questions that people have asked about synergetics, all kinds of issues that have come up in the past. I've given a list of that to Kirby. So he's going to start off with that. And then he has this amazing presentation. So we'll go through the presentations. There'll be plenty of opportunity to ask questions. While we are doing the presentation, ask the questions in the chat. But then after the presentation, we'll have plenty of opportunity to go back and forth. So this is an experimental presentation. It's a very deep topic, but we're going to try to make it accessible. Not we, Kirby is going to try to make it accessible. I will pretend to not know anything, which is not that far from truth. And I will try to ask questions accordingly. All right. So Kirby, the floor is all yours.
Okay, greetings everybody. I'm so pleased to get to do this in real time. At the end, I'll show you I have a YouTube channel, and sometimes I just talk to myself. In other words, I'll just do even this very slideshow. I have a slideshow here. I'll just do it for my own benefit. Like here I am starting to flip through them already. So I'm going to be going down through these slides. I plan to get to the end and then maybe bounce backwards and do the slideshow backwards a little bit. I'll explain more. And then also I have a lot of tabs open on my browser. So occasionally I'm using the slideshow to like anchor my talk. That's the drill down to the bottom of the slideshow, like 40 slides and then back up. But then in the side, going off to the side is when I hit my browser tabs. So I want a lively screen. I want you to see things changing. And so here's my opening slide. Now, if you look in the lower right, you could probably write that down because it's very short. Google, goo.gl, lower right, small case ZO, and then capital VYF1. That will get you access to these slides. You can even watch them while I'm showing them, but later you can go back easily. And it's just interesting that Google does not allow this anymore. You cannot make shortened links anymore. There is no new Googles, but the old ones are still working. So let's move on. So this is the Climatron in St. Louis. I took this picture myself, and I often use this slide to do autobiography because I'm introducing myself. I'm going to talk to you kind of in a meta sense. I'm going to tell you how I do my slides. Part of my ulterior motive is I'm hoping to coach some of you who are already very talented to say, hey, I could do these slides. I could take Kirby's slides tonight and I could turn around and present them. And I want to say, well, you have my permission. I'm kind of wanting to experiment with slide decks. It's kind of like folk songs, people show up with their guitars and they all teach each other folk songs. So this is sheet music. Anyway, I'm going to do a little bit of biography. I'm also going to say autobiography. I'm also going to say in this slide, I know Bucky's name is on this dome, and I know his name is on a lot of domes. And I know that there are a lot of engineers who have kind of some adored him and all this and looked up to him, but a lot of people thought he kind of was an opportunist and that he'd swoop in and take credit. Now, who does that remind you of today, right? It's like, it reminds me a little bit of Elon Musk. But I think Fuller had his own reasons. This is something I want to come back to, what the detractors say, because I don't think we fully understand the Fuller, what's going on if we don't pay attention to Fuller's detractors. So in this slide, I'll talk about that a little bit, maybe later, but let's go on to the next slide. Let's talk about synergetics itself. So there's a bookshelf with some classic new stuff, old stuff. Some of these are since he died, like the Lars Mueller publishing, the green covers over here. But you see Synergetics 2, bright and white, right in the center. And then to the left, there's 2 copies of Critical Path. There's plain old Synergetics, the first volume. So it's a 2-volume work. And you can see those are pretty thick books. So it's not trivial. I can't crank through the whole thing in like one slideshow, but I'm going to go to the core of it, I'm pretty sure, in a way that you're going to find interesting. That's my plan anyway. And it's all online. So there it is as a book. You'd have to spend money, you'd have to buy it, you'd have to find it. But if you go online, I've just jumped to the back of the book already, to the figure index, because I want to give you a sense of what it feels like, just graphically, what it looks like. And here's some figures popping up as part of this. And look at how geometric it is, right? I mean, without trying to interpret what you're looking at, just in terms of art, there's a very realistic looking kind of pipe drawing. So there's something mechanical drawing kind of aspect to it. But a lot of it is, there's his 4D symbol. So he kind of used this as a logo, kind of, he branded himself. Nowadays, it's kind of common, like Prince. This is Fuller being Prince, but he never said, just call me 4D, but he almost could have, right? So anyway, I just wanted to give you a sense. We'll come back here, maybe look at these pictures some more. There's even color plates. So if I go to the top of this section and go to table of contents, like I say, it's all online, and go down to 32 color plates. This is all interesting, very free, and you can get these to blow up. Like, I'm going to talk about something called the cosmic hierarchy, concentric hierarchy. And people have a problem with that word hierarchy because it sounds like it means top-down pyramid or something, but it really means nested, one thing inside the other. Now, I heard you talking recently in a recent YouTube about how are you going to get your heads around Bucky, and I think I heard you were going to just like, what are the big ideas? And maybe it was Maritza who said like ephemeralization and like that. And I just wanted to quickly mention at the Buckminster Fuller Institute, which I'll tell you a little about my history with this, which is I got the domain name bfi.org in collaboration with a guy named Kiyoshi Kuramiya. And I was the first webmaster for this institute, but a long, long time ago. And this is in WordPress. I have nothing to do directly with what I think is quite a nice presentation, but under big ideas, literally that's what it's called. Here's a bunch of Bucky's big ideas that you can jump into, and there's Synergetics. And if we jump into that, you will see some of our old friends here. I'll show you I'm here, but this is just the current configuration of the page. These links go to where we just came from. In other words, Synergetics online. There's also a Synergetics dictionary, but further down, Kirby Urner's page on Synergetics. So this will link to me. There's something by Ed Applewhite linked, and Struppi. I wanted to make sure we got here because you guys have done a lot of work with Struppi, I've noticed, and he's very much, I talk with him a lot on Telegram and stuff. So here's our current BFI page just to get a look at that. And okay, I'll explain this picture. Let's go back to the slides and let me go on to this slide. So what is it? What is Synergetics? So it's 2 volumes. Macmillan was the publisher. Fuller did not write it all by himself. He had considerable assistance from this guy named E.J. Applewhite. And E stands for Edgar with a G, not Edward, in case you want to Google him. And I say it's a work in the humanities, definitely philosophy. It's mostly prose, but with all those pictures I showed you. But it's not, let's do some axioms and now prove some theorems. I don't think we can call it, if it's a math book, it's only tenuously a math book. It has math in it. That's part of what we're talking about tonight. So mathematical, I say, yet mostly prose, geometrical. And if you look on the right and kind of let that animated GIF sort of hypnotize you while I talk, that's this concentric hierarchy I'm talking about. Just a bunch of polyhedrons that are nested around a sphere at the center. You could have it be that way. And if it reminds you of anything, given your culturally literate group, you're probably thinking of Kepler. Kepler did this sort of signature nested polyhedrons thing. And in its case, it was supposed to represent something. It was supposed to represent the orbits of the planets relative to one another. This concentric hierarchy here, it's just a pattern, like a TV pattern. When you're doing adjusting your TV, the old patterns, I think of this as kind of the pattern or test pattern of synergetics. Now, people will talk a lot about how hard it is to read and whether it's comprehensible, whether it's crazy, whether this is proof that Fuller kind of went off the rails at some point. Is it useful? So I would say it's controversial, even down to what is the genre. And I've made my stand. I'm saying it's philosophical and it's in the humanities, and I will defend that. But I don't think everyone who's studied Fuller will necessarily agree with me on that. Right? Okay, so let's go on. So this is a mathy looking slide, and I wanted to draw your attention that this is directly from Synergetics. Everything, it's the caption, there's a copyright at the bottom. And when I present these slides, I like to set up a little bit of attention right here. Fuller is like, he wants the tetrahedron to be his core shape because it's simpler than the cube, it has fewer edges, fewer sides, it's structurally stable. So let's just say Fuller is the champion of the tetrahedron. And wouldn't it be nice if we could have a tetrahedron also be our unit of volume? Since we're in the mood to make the tetrahedron so important, why can't it also be our unit of volume, at least in some branch of math, without touching normal math, where of course it's not, right? We don't think of a cube, or excuse me, a tetrahedron with edges 2 or 1 as having a volume of 1. In fact, if you know there's some sort of, let me just tell you that there's a theorem that says the inscribed tetrahedron, and by its inscribed, I mean it's the face diagonals of this cube. The inscribed tetrahedron, the face diagonals of any parallelepiped, but let's say a cube, any like prism, is always 1/3 the volume of that thing. So the tetrahedron is 1/3 the volume of the cube. That's not Bucky, he's not proved that. Everyone knows that, we'll say. It's been proved. So if Fuller wants this tetrahedron in the middle, the one with the thick lines labeled 2, to actually be his unit of volume, then this surrounding cube would have to have 3 times that. It would have to have a volume of 3. And we all know from high school, from before high school, that the volume of this cube, how do we normally compute it? We simply multiply the height times the width times the depth. The 3 edges, they're all the same in this case, but we multiply going around a right angle, second root of 2 times second root of 2 times second root of 2. So the volume of this cube in ordinary XYZ math that we all learn in school and we all understand is the second root of 2 to the 3rd power, clearly. So the tetrahedron inside would be 1/3 of that, second root of 2 to the 3rd power over 3. We're very far away from this being volume 1. Now, let me just clear up that when we do build this tetrahedron, we're thinking about it, forget about the cube for a second, just focus on a tetrahedron as being 4 spheres face touching each other. I don't think this is hard to visualize. And so when I say 2, I mean 2 radii. In other words, the radius of the spheres constitutes our understanding of the unit, and the diameter is 2 radii. So we can say 1 diameter or 2 radii, it's the same length that we're talking about. So when I go back to this picture, that's 2 radii, but you could erase that 2 and put a 1 there and it would be 1 diameter. And you're picturing a sphere at each corner. You can't cram spheres around every corner. You got to pick an alternating set. Okay, so just to get that clear about the 2 and the 1, diameter versus radius, here's another picture saying the same thing. And I'm saying the tension here, what seems wrong about synergetics right out of the gate and why Bucky can't do what he wants to do, which is have a unit volume, unit edge tetrahedron, is because a tetrahedron inside a cube of this length, 1/3 of the second root of 2 to the 3rd power is not equal to 1. I'm pointing that out, and it's pretty obvious. So Bucky, what are you planning to do? How are you going to make that tetrahedron in the middle of that cube be your unit? How are you going to do that? And the answer is he changes the meaning of, you could say, multiplication. It's like, when we say 2 times 4, why do we picture a right angle? Why do we make a rectangle? Why is 2 by 4 a rectangle? And when we multiply 2 by 2 by 2, why do we say that's cubing? We always say that. We see 2 to the 3rd power, any number to the 3rd power. We just say cubed out of reflex. We never stop to think that there could be maybe a different shape than the cube that could also show 3rd powering. And over here to the right, this growing tetrahedron does go up as a 3rd power. So a growing tetrahedron can be your model of 3rd powering, is Bucky's observation, and a growing triangle can be your modeling of 2nd power. So we're getting away from squares and cubes. Now I'm going to go sideways a little bit. Oh, by the way, that's the Ed Applewhite mentioned in the previous slide. Very dapper gentleman. This is a famous picture on the back of his book, Cosmic Fishing. So, like I said, he didn't write this whole thing by himself, 2 volumes and so on. His collaborator wrote a whole book about writing Synergetics with Bucky Fuller. What was that like? And it gets into more of their relationship. Applewhite often called himself Bucky's first teenage fan. It's like he tuned in Bucky and was thinking of Bucky long before, like as his whole life, he was a Bucky fan. And then he had a whole long career of his own, stuff like that. So that's Applewhite. And here's Applewhite visiting Oregon in 1996, coming to see me and my family and stuff. And he was very interested in me because I was obviously very interested in Bucky. And he wanted to know, like, the web was new. Web pages had just started to come out in the 90s. And I was like the first person to start putting out a website based on Synergetics, like what is Synergetics and stuff. And I came up with this thing called Synergetics on the web, which I'll come back to. Okay, so that's Applewhite. Okay, so let me go to a whole other place, Australia, Canberra. And this is somebody I discovered, a polymath, like you guys, 52 living ideas and so on. And with CJ's leadership and all of your leadership, you've been discussing comprehensivity, comprehensivism, polymaths fit in there somehow. This guy comes across to me as one of those comprehensivists. He's like a watercolor painter. He's got his art at this website. There's a gallery of selected works. His name is Wayne Roberts, and he's in Australia. And I don't think he ever studied Bucky at all. I can find no reference here to Buckminster Fuller. But the reason I stumbled on his thinking later is he'd proved to himself that if you have what he calls a utragon, which is just his name for any triangle with a 60-degree vertex. Now, you either have one 60-degree vertex or you have all 3 60-degree vertexes. You don't have the choice of just 2 60 degrees, and the third one could be something else because they have to add up to 180. So it's either an equilateral triangle or it's just one of the angles 60, but whatever. Think of a culture like the Avatar culture in the movie or something, a water world, where when they multiply, they put 2 sticks in the ground at 60 degrees at 2 different lengths, A and B. And when they multiply A times B, they just connect the endpoints of those 2 bamboo sticks. And that area inside, they call that A times B. So let's look at a picture like this. You've got all this equilateral triangle divided up into subtriangles. The 4 along the left side times the 3 along the right side, just close the lid, just connect the 2 endpoints. That green area, believe it or not, is 12 of these little triangles. And you can say, well, that's hard to see. That's not very practical. Squares is so much easier and blah, blah. But forget about that. Let's just say this culture, this is how they do it. It's anthropology, right? We're not going to argue with them. You can prove this is the case and so forth. So there's another picture of multiplying. And this guy in Australia, he's proving it to his own satisfaction. He's doing his geometry. But this guy is a watercolor painter, right? There's his picture, and he's proving this to himself. And what Bucky is saying is we can extend that to a tetrahedron, and I can go 2 times 2 times 5. So those are the 3 lengths coming out of this 60, 60, 60-degree corner of the tetrahedron. I'm coming out 2, 2, and 5, and I'm closing the lid. I'm just connecting the endpoints. And that's what I'm going to call my volume of 20. And yes, it turns out to be 20 of these individual tetrahedron tips. That's the volume of this thing. So we have this weird alien kind of alternative way of multiplying. We don't square or cube, we use tetrahedrons. And that's how he solves his problem of how does he get his tetrahedron to be unit volume. And this is kind of where we get into his sort of, you could call it propaganda for the tetrahedron even. But I'm going to read this because this is what people find difficult. This is why Synergetics turns people off, because what is he saying here? He's saying, this is a direct quote, geometers and schooled people, that's us, speak of length, breadth, and height as constituting a hierarchy of 3 independent dimensional states, 1-dimensional, 2-dimensional, and 3-dimensional, which can be conjoined like building blocks. And we do, we go to class and we hear about how this ant is just on a 1-dimensional string, but then this other thing is you can add dimensions. And he's saying, no, you can't add them. You can't have height without breadth. You can't have width without height. They all come together as kind of a blob. Space is, you can't go any further down. You can't take away any more dimensions at that point. So once you've got space, what is the simplest shape? What is the shape that represents that which has an inside and an outside? And you could say a sphere, but if you want to get straight edged about it and you want to talk about polyhedrons, really the anchoring shape that represents that which has an inside is the tetrahedron. And so he's saying it's 4-directional. It has 4 faces, it has 4 points. There's nothing more 4 than a tetrahedron. So let's forget this 1, 2, 3-dimensional. Let's start with space is 4D. It's another way to look at it. You could stick to the old way and also consider this new way of talking. Now, why? Why do we even care? Why would the tetrahedron be fun as unit volume? Well, it divides evenly into other polyhedrons in ways the cube never did. The cube does not play well with others compared to the tetrahedron, you could say. In other words, this orange unit volume with the same edge lengths as the red octahedron, the ratio is 1 to 4. So you could pour beans from one to the other. 4 beans, 4 cups of the orange one fill the red one. 6 orange cups, you could play cooking games. 1, 3, 4, 6, so rational, so whole number. Why don't we ever share this? Well, because no one's gotten further than this step, really. It's like 40 years have gone by and I'm on the other side of it. I don't think it's that hard, but very few people get through the eye of the camel or whatever you want to call it. It's like, so there's the beans, right? I teach this to kids. I like beans better than like cornmeal because cornmeal gets in the slats between the boards if you actually go to a school. And you can derive these volumes very visually. This is one of the color plates we were looking at. Like, how do you figure out this is exactly 6, the rhombic dodecahedron, compared to this particular cube? Now, this particular cube is important. The tetrahedron's face diagonal is the same as the length. In other words, let me say it again. The face diagonal of this cube is what's the same as the edge of the tetrahedron. We call that the prime vector. It's the main edge that we're talking about. So you got to see the tetrahedron as inscribed inside the cube, and that's where you get that 1 to 3 volume. I talked about that. We had that proof from a long time ago. Octahedron is 4, rhombic dodecahedron is 6. It's also a space filler. Now, once you've got your tetrahedron, your octahedron of volumes 1 and 4, you can start fractioning them. You can start fracking them. You can break them up into smaller components, which he called the A and the B modules, and you see them here. And once they have whole number volumes, 1 and 4, these fractional tetrahedron have whole fractions. They're like 1/24th, both of them are. Both the A and the B are 1/24th. And if you put 2 B's and an A together, 2 A's and a B together, you have a left and a right of the A, and you can add either a left or a right B, you get this tetrahedron that fills space. Like it's an irregular tetrahedron, but copies of itself without handedness will fill space completely. And so we call this shape the Mite in Synergetics, for minimum tetrahedron. It's not unknown in math at all. There are other mathematicians who studied the question, what tetrahedrons fill space? And so Fuller was kind of on that trail too. He was interested in that question and has his own vocabulary for naming some of those space-filling tetrahedrons. Now, Aristotle, he said tetrahedrons fill space, and he's always gotten flack for that because regular tetrahedrons do not. But this irregular tetrahedron I'm showing you does. So apologists for Aristotle, they point out that in the ancient Greek, he never did say regular, did he? So Aristotle was right, or something like that. We name this shape. This is made out of 8 mites. It has the same volume as the tetrahedron, the unit volume tetrahedron. This is also a space filler. It's an oblate octahedron, but we call it a coupler in Synergetics. And it has the same volume as the tetrahedron. And so when you play with these shapes for a long time, within this new system of the concentric hierarchy with its particular volumes, you develop that right brain fluency that I think Synergetics is unappreciated for delivering. Do you want to do any questions now at this point?
Yes. So firstly, I have a few questions, but folks, if you have questions of general nature, go ahead and put them in the chat at this point. So first, could you elaborate a little bit on, firstly, I want to say this is a great presentation. This was wonderful. Excellent start. Couple of just quick questions. When you say that it's fills space, this is a space filler, what exactly do you mean? Can you elaborate?
Yeah, like without gaps. So like bricks, they fill space with no gaps. But a tetrahedron, a regular tetrahedron, if I give you a whole box of them, there's no way to glue them together face to face that you won't have a lot of empty space in between, right? They don't by themselves pack together to fill space without any holes or any gaps. Now the octahedron and the tetrahedron together, the two of them together, they do fill space. I can show you, let me show you. Here's a Bucky original picture, by the way. I don't know if you can quite decipher this, but these blue shapes, those are the 12 diamonds faceted rhombic dodecahedrons. And there's a ball inside of each one. The balls kiss each other through the diamond centers. Those are our volume 6, you could say, rhombic dodecahedrons. They fill space. You can have a whole box of rhombic dodecahedrons and glue them together, and you will have no intervening space. And when you do that, the balls, you're basically, when you do that, the balls are going to be in what's called the CCP, or cubic centered packing conformation. Here's a ball inside of one rhombic dodecahedron. If I pack those rhombic dodecahedra together, the balls are going to end up looking closest packed. Let's see. The CCP looks like that. Further down. 12 balls around a center ball. I know you guys went and interviewed Tom Miller and stuff. I'm just not finding the exact picture I want to find, but okay, so that's what I mean. Do you understand about space filling? Yeah.
Perfectly. So it fills space without any gaps.
That's it.
That's the whole thing. Okay, perfect.
That's it. That's it.
Okay, next question. Now, the starting point of Bucky is dramatically different from the starting point that the Greek geometry uses. Can you talk a little bit about that? Instead of starting with points, kind of these abstract entities. Go ahead.
It's a little hard for me in my studies to figure out when did I'll call it a dogma, but we all believe it. When did they start saying space is three-dimensional? In other words, does Euclid ever say space is height, width, and breadth? Those constitute the 3 dimensions of space. I don't know. It's not like an axiom. It's something we all agree on. But the history of Greek geometry, I'm not sure what the Greeks would have thought of this. I think they would have accepted it. I think everything I've shown you so far, if I sat down with Plato in his symposium and went through all what I just went through, I don't know what, I think Plato would go, okay, that's pretty cool. I didn't know that, but it feels Greek to me. In other words, it's not entirely anti-Greek, but then Synergetics does, Fuller's point is we have telescopes now, we have microscopes since Greek times. It was kind of metaphysical, their geometry, and they had things like perfect solids, the idea of a perfect, impermeable, absolutely continuous solid or manifold that has total continuity, as we'd say in math. And Synergetics is not like that. Synergetics is nothing really touches anything else. There are no solids because when you use an electron microscope, you can fly through marble. It's like everything we call solid is really tensegrity. It doesn't touch. So Fuller has this different feel about his geometry that's, I would say, not as Greek because it doesn't have that solid feel. But a lot of it feels kind of Greek. Like, I don't think the Greeks would be too freaked out by some of this. I think of Synergetics as kind of a Neoplatonism. It would have a much less of an uphill battle in like the 1600s than it's having now in the 20th century and the 21st, because we don't think in terms of polyhedra much at all anyway now. We've kind of lost that. Kids get it in 10th grade, there's geometry, but it's all in the back of the book, the polyhedrons. So they do plane geometry, no time for the polys, and then they're gone. You don't have them in your life. And so sad. And even philosophy used to have more polys. So I think of Synergetics as bringing polyhedra back into philosophy where it belongs, where they belong. So shall I go on about the T and the E modules?
Let's see. I think Becky has a question. Let me go ahead and unmute so she can ask it herself. Go ahead, Becky.
Oh, it was actually Chad's question.
Oh, you're
maybe he
responding
would
to that.
like to.
That's fine. That's fine. Then let's continue then.
Okay, so just to round out, what is the content of Synergetics? What does he talk about a lot? And he wants these volumes. They're not all whole number volumes. Sometimes you'll hear people say like Synergetics has no irrational numbers, or that Fuller didn't like irrationals or something. This is not the case. There are a lot of irrational numbers. But this rhombic tricontohedron, it's just got, okay, that's one way to name it. It's got 30 diamond faces. And once we're in the realm of tetra volumes, so now we're talking about the tetrahedron as our unit of volume. That's just taken for granted now. We almost forget that most of the world uses cubes. Oh yeah, I forgot. But so what is the volume of this thing? Turns out to be almost 5, so close to 5. And so what would we have to change the radius by in order to make this exactly 5? And this is something Fuller researches in great detail. And this number at the very bottom, 0.9994, that's just the radius of the rhombic tricontohedron if we want its value, its volume, that is, its tetravolume, to be exactly 5. And so he's very excited to have discovered this like hairline fracture between two rhombic tricontohedrons. One it's exactly 5, and the other one precisely embraces the sphere of radius 1. So this is something he gets into. The thing is, the T modules, which is 120 of them, if the rhombic tricontohedron has volume 5, what's the volume of the T module? 1/120th of 5 is 1/24th. So the T module turns out to have the same volume as both the A and the B module. So in terms of mnemonics, just trying to hold something in your head that will help you as a sculptor, designer, somebody who knows like right brain geometry stuff. This is an interesting compact way, and it has this little hairline crack in it, which Fuller talks about. Here's a picture. He's saying, oh my gosh, if we were talking about something that's 10 inches deep in terms of radius, the difference between these two rhombic tricontohedrons would be a 200th of an inch difference between perfect volume 5 and a little bit more than volume 5. And you can express it in closed form with phi, second root of 2, other stuff. So there's been some research to get this all straightened away. Now I know Tom Miller talked about the S module. This is the last one of the modules. In fact, you can remember them by reordering the A, B, S. It turns out to spell beast, B-E-A-S-T. Maybe that sounds diabolical or something, but it's easy to remember. And this S module, it crams in between the octahedron, which is on the outside, and then there's a face bonded, like flush with the faces of the octahedron is an icosahedron. And this is a well-known geometric relationship. I'm not saying Bucky discovered it or anything, but he did carve up the difference between the two, name that the S module. 24 S modules packed around that internal icosahedron make the octahedron, and then he goes on to compute its volume and so forth. And some of the research since Fuller passed away has to do with taking phi scaled S modules. Like, okay, so here's an S module. To phi scale it is to lengthen all of its edges by 1.618. So it goes up a size. You can think of beer mugs. When you go into this bar, they give you the standard beer, but if you go phi up, it's a much bigger stein. And if you go phi down, it's like it shrinks. All edges shrink by phi, and therefore volume goes down by a third power of phi. And we found that if you add these different powers of the S module, you can get the whole number volumes that we were talking about already. So it's very interesting that way. We have a formula for computing the volume of any tetrahedron in tetravolume. So it's not that it has to have 60, 60, 60 degree corner. It can be any random tetrahedron. Just throw it out, take the lengths, put it into this formula or one of several. We have more than this one, and we'll get the tetravolume out directly, right? We don't have to first get the XYZ volume and then convert it. But there is a conversion constant. In other words, kind of like Canadian dollars versus American dollars, everything kind of has two prices. You can set up a constant between what Synergetics would say the volume of this thing is versus what normal math would say. And it all goes back to our first or second slide about that cube, where normally it would have second root of 2 to the third power, but Synergetics says its volume is 3 because of how we multiply. And I went through that whole thing. So there is just a straight constant for going back and forth between Synergetics volume and what we'll call normal cubic volume. And I have a lot of slides about that. This slideshow gets into that. What I'm doing in this whole section of the slides is saying once you are over the hump and are allowing yourself to have a unit volume tetrahedron, then you have kind of a new space to play in, a new sandbox. And this sphere packing here that you see at the center, I'm going to call that the CCP for cubic centered packing, and that's what the mathematicians call it. That's the official name for this. So it starts with a nuclear ball and then 12 around it, and then 42, and then 92, and then 162. And that's called the cube octahedral numbers because the shape doesn't change. You see a growing cube octahedron even as more and more balls are packed around in layers, and that makes a sequence of numbers. And this is all known to math. This is not like Bucky discovered this or anything. He's just organizing it in a very intuitive and intelligent way and connecting it up with architecture so that from this, that the crystallographers also know about. This is Arthur Loeb. He's a contributor to Synergetics.
Kirby, let me ask you a question.
Sure.
You made a very intriguing comment. You say once you get comfortable with it, you can start playing with it. And so the question I had is, how is the feel of playing with Synergetics, with these objects, different from playing with the XYZ axis? I will give you what it feels like to me, and then you can correct me and elaborate because you have a lot more experience doing this. What this feels like is that you're actually dealing with objects that are there in reality, and you are actually working on configurations of these, and you are building things off that. So there is a groundedness to all that. All the imagination that you're doing is grounded in these forms which are actually there, as opposed to these axes which actually do not exist. These are like concepts. So this is kind of starting with things versus starting with abstractions. Is that a fair way of looking at this?
Well, I think that I'm thinking about that. I mean, we could be more concrete about the way we XYZ. When you think about it, XYZ is, you compute the volume of these like boxes and then cylinders and spheres, and it's very much in the textbook usually. But like with Synergetics, like I have this magnetic cube. If you see it, it's in my picture, and I can take it apart, and each one of these little segments here, 24 of these make the cube, and this is what we called a mite a second ago. So if I were working with kids, I could give them this magnetic cube, and this could be my volume 3. So in a way, I'm just being different because I'm using a cube and not making it volume 1, and that's already kind of strange. People make art kind of like if you use a inkjet printer, maybe this is kind of how you would be thinking. This is a friend of mine did this. He's into this kind of stuff. I'm not really sure I'm answering your question. I think it also depends on the kind of teacher and the kind of workshop it is, because like people like Struppi who are really hands-on, we feel like, well, I never got that, so it must be XYZ's fault. But I feel like people who work in a shop a lot and get trained on machines, they get the hands-on, they learn to think that way, right? I feel like because of Bucky's background, he did a lot of hands-on stuff, that there is that somehow that feel to it, that, there's a real pipe in there to weld or something like that, because that's how he thought.
Andreas had a comment. Andreas, could you go ahead and speak about this?
Yes, I'm very, intrigued by Kirby and this worldview and like the sandbox. But I have this community where he participates, Math for Wisdom, and I think about the way I kind of take what he says in my way would be that cubic geometry is about independence. So height and width and breadth are all independent. They have nothing to do with each other. Whereas when you take a tetrahedron, every vertex is connected to every other vertex. So it's completely about interdependence. And so then your insight, I think, is very nice in that way. It's saying like, see, if it's about interdependence, it's saying like, this is, and it relates to other things that are. Whereas if you're talking about cube, it's like saying, this may be, but it has nothing to do with these other things. And so each point of view has its advantages. But I think what Kirby, maybe Buckminster Fuller is saying, like, our whole world is highly influenced by this box thinking, by this kind of like, so the kind of individualism we have in the type of, the whole capitalism, the whole society is about like, this has nothing to do with that, right? Whereas imagine if we had a whole different math and everything was about interdependence, that you could not have any point that was not connected to all the other points. So you need an extra dimension to that. So you need to believe that we're living in 4 dimensions. And so the issue is that this is kind of all in terms of answers, but it's not really formulated in terms of questions. And so I have like a PhD in math, like the idea of having like, we don't think in 3 or 4 dimensions, we think like in n dimensions. You can have as many dimensions as you want. So I don't think Buckminster Fuller was really into that whole ability. So he kind of, there are reasons to believe that 3 and 4 dimensions are the most interesting. Like if you look at the Poincaré, like certain things become easier when you have more dimensions. Certain things are super fascinating when there's only 3 or 4. But you see, this toolkit, it's like Kirby said, it's a sandbox,
Yeah.
So if you want to play, it's one more sandbox. That's great for high school students. If you want absolute truth, like what I'm trying to do, like, I don't want a sandbox, I want the truth. So that's
wonderful. Thank you, Andreas. Really appreciate it. We'll have a more chance for comments once we are done with the presentations. Then we will go ahead and I'll come back to you at that point.
I think that was a very, very good remark. I always go to Buddhism and the Asian prajna paramita or whatever, the interdependence, codependence of all things. And this idea that the dimensions can't be really teased apart and that height, width, and depth are always there. It's kind of the Descartes cogito. It's like, close your eyes, they're almost Kantian. Try to just be. Can you really shed width, but you still have height or something like this? In a way, it's just a different beginning. But I wanted to, and Alexander Graham Bell, by the way, he came up with the same thing. And people say, oh, Bucky just ripped him off, I guess. Well, here he's writing the prologue. And he says, you know, I thought the guy invented the telephone. That's all I knew. I didn't know he was all into this kind of stuff, which is the same thing Bucky was into. In other words, when you pack balls together the way we're talking about in the CCP, which is part of crystallography, part of chemistry, it's not unique to Bucky. It's just he calls it the isotropic vector matrix, IVM, which is kind of smart because it comes out with just 3 letters like XYZ. So we're kind of saying XYZ and its king cube and IVM and its king tetrahedron or queen tetrahedron. XYZ and IVM kind of compare nicely with each other as each has 3 letters. And here's Alexander Graham Bell kissing his wife through an isotropic vector matrix, we can call it. That's what Fuller called it. My friend Sam is really into a building method, way of creating structures which have some flexibility, but also load-bearing capability using this kind of CCP, but the balls don't actually touch in his system. And we did a whole art gallery. I have some slides about that, and YouTubes and such. So yeah, XYZ, I would call that like the jack. It's got 6 spokes. We say there's only 3 dimensions, but the positive arrows, the positive vectors, are helpless to reach on their own, all but the first quadrant in XYZ. We have 8, not quadrants, I'm sorry, octants. XYZ divides space up into 8 octants, but the positive basis vectors all by themselves can only reach into the first octant. So we need a negative of everything, but those secondary spokes don't get to be called basis vectors. They are the negatives of the positive elementary vectors. So we say it's only 3, but the other 3 have to do the same amount of work. In a way, we're not giving them credit. I would say the 6 vectors of the XYZ system are here. It looks like a jack, and there are 6 of them. Now, with this other coordinate system I'm going to introduce, we only have 4 vectors coming out from the origin. So it really divides space only into 4 quadrants, not into 8 octants. And there are only 4 of them. And this, again, is a nice picture of what we could mean by 4D. We're saying 3D space could also be called 4D. You want to call 3D space 3D because of XYZ and because of height, width, breadth. But we're saying we can't separate height, width, breadth. It's all a tetrahedron. Let's call it 4D. And here's our coordinate system for doing that. And we have all positive coordinates, and we have 4 tuples, 0, 0, 0, 1, 1, 0, 1, 0, stuff like that. So we have 4 coordinates for each point in quadrates. And we add them the same way you add normal vectors. In fact, all the regular vector algebra applies, you could say. What turns out to be interesting is if you pick any 4 IVM balls, any 4 CCP balls at random, and connect them with edges to make a tetrahedron, you will have a whole number volume in tetravolumes, something we don't get when we're doing all cubes, right? The idea is the cube XYZ system was too simple. Instead of having octahedra and tetrahedra packed together to make the IVM, which is the same as this ball packing, that's complicated enough to address nature. But XYZ is kind of awkward. It doesn't really fit what nature's doing. Notice how the Pythagorean theorem could just as well be expressed with equilateral triangles as shown in this picture. We never see that, but it's true, right? I'd say there's a aversion to letting the tetrahedron even be king for a day because people are afraid it might keep the crown, right? So let's just forget about the tetrahedron and stick with the cube. But I feel like the quadratic coordinates in a rhetorical sense, in a sort of battlefield sense, are helping win more attention for Synergetics because it's interesting to have another coordinate system. It's all programmed in Python. And you can make it be that all the centers of all the IVM balls have whole number integer positive coordinates. Nothing like XYZ can do. Now, here's where we're going to get to Andreas's main point. This is from Coccider. And I'll pause for questions after this and the next slide, and then we'll pause. So Coccider is the man to whom Synergetics is dedicated. Fuller says this was the greatest geometer of the 20th century. And he's a Euclidean geometer, but extended Euclidean. He's at the University of Toronto. He's Canadian. There's a new bio by Siobhan Roberts about him, she also did a bio on J.H. Conway. Anyway, Coccider is telling us in regular polytopes, this has nothing to do with Bucky, by the way, that the time machine idea of four-dimensional, you're getting that from Einstein. You're thinking 3D plus time equals 4D, four-dimensional. And then there's me, Coccider. I do extended Euclidean, and that's like Andreas was saying. I can have as many dimensions as I want. I have n dimensions, and they're all equally spatial. There's nothing, you don't single one of these out and say that's time. And in Minkowski space and all this Einstein stuff, we actually treat time differently. It's not the same algebra as n-dimensional Euclidean. So here's my summary of what I would call not sandboxes, but namespaces. These are contexts. These are namespaces wherein the meme 4D occurs. And if you go back to the beginning of the 1900s, there's a lot of ferment around 4D. People want to talk about the fourth dimension all the time. And I'm arguing it never did settle down to just one meaning, that we all have the same meaning for 4D. It depends on the context. Are you talking about relativity? Are you talking about n-dimensional Euclidean geometry, which is a lot more like machine learning? We have 20, 30, 50 dimensions easy when we do machine learning, and that's linear algebra, just as ND linear algebra. No problem with that, works great. 4D, the way Bucky means it, it's a new namespace, a different one. And there, the tetrahedron is king and space is 4D, except it's pre-frequency 4D. When we add frequency, that's where time energy comes in. In other words, we say all these eternal Platonic stuff, the tetrahedrons, all these things, pre-frequency is like before we put them in a particular situation as special case. When you're looking at an actual sculpture of a tetrahedron, a rusty one in the middle of the forest somewhere, that's a special case tetrahedron. That's adding frequency to 4D. So 4D is like primitive, nothing added, no energy, no time, eternal. And then you add dimensions on top of that, like time and energy, to get real special case. I'm just telling you the language that Synergetics uses. I'm not trying to say, oh, you have to think this way, you have to believe this way. It's no, Bucky is a futurist, a philosopher, and he invented a language. He made up a way to think, and he uses a lot of what we would call science words, but he's just using the dictionary. He's like, I'm going to use the word gravity the way it makes sense for me to use gravity. And it's like, this is not physics. It's work in the humanities. He's not trying to duplicate or popularize what Einstein was doing, but he got to be friends with Einstein. And Einstein liked the first book he wrote, 9 Changes to the Moon. So Fuller gets close to Newton. He sounds like Newton when he talks about gravity in connection with Newton. So Bucky's kind of a chameleon. His meaning of gravity seems to get closer to whoever he's talking to at the time, we could say. So to wrap up, what I'm going to do with the alienness of Synergetics, the fact that it's not the way we learn anything in school, is I put it off in a science fiction story about ETs or Martians who come to Earth and they want to collaborate with Earthlings on hydroelectric dam building. And this is a very poor drawing of a hydroelectric dam under construction. And you see that the concrete, they have to pour it and gradually build this wall up higher and higher till it blocks the water. The Martians think in terms of unit volume tetrahedron. And the Earthlings, they have to kind of adjust, and because they're collaborating with the Martians, right? So the science fiction story is kind of like our Earthling kids need to go to a special school where they learn to think more like Martians. And part of what they learn in that school is how the Martians have to get trained to think more like Earthlings. It's like what we teach the Martians is about this flappy tetrahedron, this tetra book, we call it. It's got one page and two book covers. So the book covers are open flat, they're equilateral triangles, and this page can go back and forth, wag between the two, creating two tetrahedra in the process. And we use this so-called tetra book and the math around it to explain the whole business about the synergetics constant and how we go back and forth between unit cube, which would be over here on the right, with all edges r equals 1. There's our unit cube in XYZ. It actually has the same volume as if the tetra book had its page standing straight up vertically, edges 2. What's true is the tetrahedron of edges 2, in other words, 2r, 1d, even though that's twice the length, right? I'm talking about a tetrahedron, regular tetrahedron with twice the length edges as that of the green cube over here, it still has smaller volume. Even though the edges are twice as long, because it's so sharp, because it's so unsphere-like, it actually has a little bit less volume than the cube. It's like 6% different. It's a little bit smaller. So this is how we go between Synergetics volume and XYZ volume. You see the number down here to the left, right? So we can go back and forth between them. So that explains. So now I'm back to sort of that original slide, and I'm saying, so that's how we get around this problem, that this cube could never have volume 3. It does now, because we have a different way of multiplying. We have a different way of making the tetrahedron be center stage. And this goes all the way back to 1950. I'm showing where he's figuring out the same kind of numbers that we see much later. Synergetics is a progression. It's like a snapshot of where he was throughout his career, all kind of piled together in the way Applewhite would do things, which is kind of create index cards, 8x5 size, and pull out synergetics from this organization of cards over time. So again, let's stop. Any questions? Where are we at?
Okay, Kirby, I think this is a very good point where I want to get people in and to have them talk. So folks, is that okay, Kirby? Okay with you?
Yeah, sounds
okay.
Good.
I know that you have a lot to say and we would love to have you back, but I want to let people engage with this material. And let's see where everybody is. So folks, two things. If you're familiar with Synergetics, please go ahead and type an exclamation mark to make your comments. Add your own 2 cents to how do you approach Synergetics, and anything that you have to say about everything that has been presented. Would appreciate that. If you're not familiar with Synergetics, please ask questions. So go ahead and type exclamation mark in order to speak. I'll give a few seconds here. We're going to start with Chad. Chad, what's your question?
Hi, I think my first question would be, we have a lot of software programs out there like AutoCAD that is based on X, Y, and Z. Is there any software that is based on the 60-degree 4D grid? Or can those Bucky formulas be used to convert the grid into something that's useful?
Go ahead, Kirby.
Yeah, we have, okay, so I like to make these ray tracings like I'm scrolling through right now. And these all, they could be any kind of CAD program, but this is, and it's all XYZ. Everything that the POV ray, it's called povray.org is where it hides. And it's a free open source ray tracing program that you have to script it. You have to tell it what to put where. And what I do is I write a lot of my code in Python in quad rays. In other words, I use that coordinate system I was just talking about. Let me be clear though, that Synergetics, the 2 volumes, didn't have any of that Quadratic stuff in it. That's all since in the last 40 years, and I don't take credit for inventing Quadratics, but I have done a ton of Python around it. And so I have all my spheres with whole number positive coordinates, and I push a button and it renders in normal XYZ coordinates. In other words, I can convert back and forth. So it's in a way, I think of IVM coordinates as just an API on top of XYZ coordinates. It's just a different dashboard where my basis vectors are to the corners of a regular tetrahedron, then your basis vectors are the XYZ ones. In fact, it's like all the 12 directions from a center ball to the surrounding 12 balls. That's just permutations of 2, 1, 1, 0. In other words, in quadratic coordinates, there's 12 ways to do 2, 1, 1, 0. There's 2, 0, 1, 0, 2, 0, 1, 1, 1, 2, 0, 1, like that. There's 12 different ways. Those vectors turn out to be the directions from any ball to the 12 balls surrounding. So you can see where I'm having fun doing CAD, you could say. I am doing this, what you're asking about. I do it with Quadrates, and I take Synergetics to be my inspiration for that. Quadrates, by the way, is in Wikipedia, and you'll recognize these graphics, right? Guess who, right? And I say, if you understand quadratic coordinates, you'll have a better understanding of Synergetics. And I put that in a sentence here, Synergetics. And if you click on that, here we are, Wikipedia Synergetics. And here I want to draw your attention to the volumes table. In other words, I hinted at all these different volumes, but here we have a nice, we can get them all together in one view of what the volumes are for the different modules and so forth. Okay, what else?
Kirby, could you put your contact information or how people can get in touch with you in the chat, so that if they want to follow up with you on any of the questions, they can do that. Next up is going to be Richard, Dave, and Andreas. Richard.
Yes. Hi, Kirby. My interest in the three-dimensional aspects of XYZ comes from the notion of observed independence. So a three-dimensional world that we live in is the XYZ axis, and the observer is independent of that. And I think in the diagrams that if you put the fourth point, you can't find a way to join those other three unless you change from 90 degrees to 60 degrees. And once that's done, then the notion of the observer and the observed then becomes interdependent, and one affects the other. From the kind of presentation you made tonight, is there another way of trying to understand how you have to bring the three-dimensional XYZ axes into a four-dimensional 60-degree system in order to understand observed interconnection or interconnection or interdependence?
Go ahead.
Well, I think a lot depends on your own inner headspace too. It's like you're not different from your own thoughts or imagination. So if you grow an IVM in your mind's eye as where you're, let's call it a sandbox again, but if you're thinking the way we do in Synergetics, you're looking at different cartoons a lot of the time, right? And I think what we've seen in the last few decades is a gradual emergence of 60-degree, 120-degree aesthetics over XYZ. XYZ is being deprecated in a way because organic chemistry is what it is. It's hexagons, it's pentagons. Nature is 60-degree based more than it is 90-degree based. So I think, I'm not sure I'm quite answering your question. I just think that the Synergetics style of thinking is a harbinger and it's just a little ahead of its time. We're all gradually catching up. And it's not because of, quote, Bucky. It's because as humanity becomes more competent, we learn and we see that the universe is more like hexagons than it is squares, if that makes any sense. I wanted to say this slide right here. You were mentioning that we just know that space is XYZ, as if you could just look around and it's like obvious. I think when you look to the corner of a typical room where you have two walls and the ceiling coming together at 90 degrees, you look at that corner, it kind of reassures you that, oh yeah, that's XYZ, that's the way space is. But Darcy Thompson here, a well-known guy, right, biologist and so forth, he's writing here to Whitehead in 1918. And he's saying, you know, if I'm just swimming around as like a flatworm, I'll get to this other picture, then I don't have any sense of 3D. And in fact, he says, I'd be tempted to say 4-dimensional. I just think this was such an amazing quote. And I'm pretty sure that Fuller never would have seen it. 4-dimensional space. He's talking about ordinary space, right? Why do we say it's 3-dimensional? Why are you so sure that it's 3-dimensional? I think it's because you were taught that in school and probably no other reason, right? I don't think you have any good reasons for thinking that, only bad reasons. But we could argue, but no one ever does argue about this stuff. I think it puts more power in the hands of children if we allow them to question our dogmas. And so I like to bring this Fuller stuff to the surface because it is questioning authority that we're not used to questioning. No one questions XYZ. No one questions space as 3D. So no one says 2 to the 3rd power is anything but 2 cubed. No one ever thinks that that's cultural, that's anthropological. Also, Carl Menger, a dimension theorist, he comes up with this thought independently of Fuller a long time ago. This is 1949. And he's saying Euclid didn't think that Euclid's assumptions about points, lines, and planes involved a twofold idealization of the relations between small dots, rigid rods, and flat boards. So you see, in calling them dots, rods, and boards, he's saying they have thickness. They all have the same dimensionality. Dots, boards, rods have an inside. You can roll them out long and thin. Take a tetrahedron of dough, like bread, a clay tetrahedron. You can roll that out into a very long line. You can roll it up into little tiny dots. Those are your points. Or you can make a cube out of it. You can make any other shape. They're not different dimension. They're all the same dimension. And he called this a geometry of lumps. And it's clearly not Euclidean geometry. It's not what we're taught. And I'm not saying we have to throw away. This is not about, oh, Bucky's right, we have to think different now. It's no, you've got another namespace, this one. Tetrahedron is minimum shape, RBF. Go there and play. Now, if you think there's one namespace to rule them all, that's philosophy that you could, you know, is there only one truth, or are there multiple namespaces that we could always have? We always have access to other ways of thinking, perhaps. Also, Synergetics anchors the use of this word system quite a bit. So he has a very technical meaning. Coming from a philosophy background, like I studied Wittgenstein at Princeton a lot. I didn't get into Fuller until after I graduated, but I learned to see that the meaning of a word comes from how it is used in a game-like way. So that Fuller uses words at length in long books because he's putting his own spin, his own nuance on that. It's like when you invent your own language, you need to give people a lot of like examples of how you're going to use it. And there's a whole 4-volume dictionary on top of Synergetics, also by Applewhite, that chronicles Fuller's odd, unique, I think almost private way of using his words. He's very out there. He's very remote. He's very different. And all this stuff feels very alien. So the question comes up, how quixotic is it to champion Synergetics? Like, what do you have to do? Do you have to
let me do one thing, Kirby. There are a few more questions. I want to make one quick comment, and there is a question from Dave and a comment from Andreas, and then we'll continue. So I want to point out that Darcy Thompson is an amazing figure, and that quote is actually speaks a lot because he is the authority. He has this giant book on growth and form, where he studies how things grow in biology. It's an amazing, amazing study of how life grows. So him talking about this is very, very significant. So I would recommend that. But again, it's all about Darcy Thompson as a biologist is looking at how things grow. And he's saying, okay, we need a way of conceptualizing space, conceptualizing things based on how things grow. So I think that's very, very significant. Thank you for bringing up that quote, Kirby. Next up is going to be Dave. Dave, go ahead.
Thanks, Shrikant.
Go ahead.
Very interesting lecture, Kirby. I think of geodesic domes when I think of Bucky. I don't know if you want to go there or not, but there was a sphere, and I believe you said it had 24 diamond faces. And I've seen several domes, and the other comment I would make is that I believe a triangle is more stable than a diamond. Of course, your tetrahedron is made of triangles, but I think all the geodesic domes I've seen have pentagon faces, which I guess are made out of 5 triangles. Is that something you'd like to comment on?
Sure. Joe Clinton and a lot of other people have spent a lifetime elucidating the dome concepts. And yeah, there's 12 pentagons usually. This is true also of C60, the carbon molecule that was discovered after Fuller died. That guy Applewhite, he went around and celebrated, or he was glad that they named it Buckminster Fullerine. This is that guy Applewhite talking about it. But you see there's some pentagons. Well, it's a soccer ball. Soccer ball has 12 pentagons. And this has been known, and people sometimes get pissed at Fuller because he had a patent, and some Canadians wanted to get into that ray dome business, building the dew line domes across northern Canada. They were looking for missiles coming over from the Soviet Union or whatever. Those were all put inside of Bucky balls, Bucky domes. And Bucky had a patent. And Coccider, that guy I was talking about, the university professor, he's Canadian. He's like, who's this American imperialist who thinks he can own the geometry of nature? In other words, what you're talking about, these geodesic domes, they're spheres. See, Fuller's domes were always part of spheres, and he did study the spheres all the time. And it's like polyhedra, when you spin them really fast, that's where you start getting great circles. So the way to connect the domes you always think about when you think of Bucky is think of spheres first, not just partial spheres, domes, in other words. Think of the whole sphere, and think of how the great circles that crisscross all over the surface come from polyhedra inside, spinning really fast around different axes. That's how they're connected. Spin the polyhedra. What I like to do is bring it all down to his polyhedra, the static shapes, because I don't think most people go there with Bucky. They stop at the dome and they think of him as the geodesic sphere guy, and they don't realize that it keeps going down into static polyhedra, which is more Greek. It feels more metaphysical there and stuff. It's a part of Bucky I want to bring more into the foreground. So I don't emphasize the domes.
Thank you. Thank you, Kirby. Next up is going to be John, followed by Andreas. John, go ahead.
Thanks. Yeah, I have a question or comment about looking at the number of points and the number of dimensions in reality, really. So I like to make the distinction with realities with music. So we can represent music on a CD with binary information, but we can't actually hear it. We have to convert it into non-binary in order to hear it. So there's an important distinction between the way we think about something, or the way we represent it, and how it really is. And I'm thinking the progression of looking at points. So a point by itself has no dimension. A second point has one dimension. You have a line, but it can't exist in reality. So you have a third point, you get a triangle. Again, you can't have that in reality. In the fourth point, you finally have an inside and an outside. But until you have a fifth point, you don't know which is the inside and which is the outside. So to me, you have to have the fifth point inside, which gives you the quadra from the observer out in the 4 dimensions. And each of those dimensions must be interdependent. So my thought is that even 4 points cannot exist in reality. It's not a real thing. You need the fifth point in the middle to create something that can exist in nature. Do you think that's useful?
I think it is. I think it's very true, especially in kind of Western conceptioning, that we forget the observer. And this goes back to the previous question also. And in like ray tracing and stuff, what you have to do to get the art, like I've been showing you, is you always have to define exactly where is the camera, where is the point of view. And when we learn math, we're often like looking down at an XY plane and we see the positive numbers going off to the right on the x-axis. But if you were to take your camera, your point of view, and go around to the other side and look back from the other side, then the positive numbers would be going off to the left. So it's like we deliberately forget that there's a point of view on these things and think there's some kind of God's eye view that we're occupying, that we're not bound to a specific angle on the action, but we are. And I think we often want to forget that, the omniscience that comes with forgetting that there's a camera and that you have a point of view always. I'm with you on that.
Thank you, John. I really like that observation. When we talk to Tom Miller, he uses the term skeletons of polyhedra. So skeleton means you have the center of this tetrahedron and you have these lines coming from the center to the vertices. And it actually is the identity of the thing. You know, that's how it's going to grow. That is, so it's like seeing it in its essence. You know, you're seeing the center of it and you're seeing how it kind of spreads out from there. So I think it's a, thank you for bringing that up. Next up is going to be Penny, Mike, and then Andreas. We give priority to people who have not spoken before. So Penny, go ahead.
Okay, I just had a question. I think when you was talking about the Mite, you said the Mite was the space filler, so the thing that you could put inside and there wouldn't be, any areas that weren't covered. Is the Mite the same shape always, or does it vary depending on what you're sticking it into?
Yeah, when Fuller talks about the Mite, he means a very specific shape, which I can hold it up in my box too. It's got right angles. It's just exactly, it's a tetrahedron with certain exact dimensions. And because it makes a cube, 24 of them, without left or right. By the way, the game that the mathematicians play, and only a few have researched this, but I know about them, a guy named Goldberg, Somerville, others, they asked themselves what tetrahedrons without left and right will fill space without gaps. It's a known question. And one of the answers is what Fuller called the Mite. But I don't think he was aware exactly of their research. Although Goldberg keeps coming up in Fuller's writing, like not that he cites Goldberg, but Goldberg's in the same exact neighborhood as Fuller. In fact, if you look up Goldberg polyhedra, you'll see those geodesic spheres we were just talking about that have the 12 pentagons that we associate with Bucky. Those are also called Goldberg polyhedrons. A lot of what's in Synergetics is well known. It's just organized a little differently.
Thank you, Kirby. Next up is going to be Mike. Mike, what's your question?
You mentioned Carl Menger and his Menger sponge, which was a generalized n-dimensional polyhedra. Have you looked at what's being done in the molecular molecular physics area to try to do protein folding. Carbon has a valence of 4, which is kind of like the 4 vertices of a Buckminster's thing. And Wolfram has taken some of that and come up with an analytical way of coming up with some of these things. And I just wonder, in particular, for protein folding, have you immersed yourself in that approach? And what have you done with Carl Menger's Cantor set sponge?
Well, this guy, Carl Menger, we do mean the same Carl Menger. I know that this is the same Carl Menger as the Carl Menger sponge. This essay that he wrote is from something called Einstein, Philosopher Scientists. And it came out a long time ago. And it reminds me that at the time, Einstein was considered a philosopher. But today, if you were to go to the university, they will not put Einstein on the philosophy reading list, right? So this is kind of from a different time. It's the same Menger that we're both talking about. And in fact, coincidentally, I had read this in the library, taken notes about it. I was already familiar with this essay. And then it turned out I knew his daughter. She lives right here in Portland. And so I was friends with Eve Menger, one of his daughters. I don't know if he has other daughters. But I just feel like what I'm showing with this slide and with the Darcy Thompson one is that Fuller was not operating in a vacuum at all, and including with all that sphere packing. That was a major obsession of the 20th century. And writers like Conway, mathematician Conway, he definitely goes into n-dimensional sphere packing and all of this. That's the 4D of Coccider. And I don't mean to dismiss or in any way say that's not an important area. And it's not like Synergetics is here to say, okay, step aside. I'm here to save the day. It's not like that. It's more like, here's a very interesting, different way of thinking that Fuller contributed that for the most part, we're ignoring completely because Synergetics is a little too dense and nobody gets paid to read it. It's like if you're a practicing professor, you've got to keep up with your field. Synergetics doesn't neatly fall into anybody's purview. So the time just keeps going by. But people like me, I dive into it and I say, hey, there's stuff here. This is a gold mine. We should do more with this. That's my feeling.
Thank you. Next up is Andreas. Andreas, go ahead.
Yes, I'm blessed that Kirby and I are exchanging letters at the Math for Wisdom discussion group. I put a link if anyone wants to join us. And so I'm just fascinated by his mental energy and the namespace work sandbox, where to show that for high school students, like you have alternatives, and that they have big implications. And so what John Brett asked, see, I like that because I do believe in absolute truth, which is a big taboo. And I do believe that to have that namespace to rule them all, as Kirby said, we have to fundamentally think not in terms of answers, but in terms of questions. So like my challenge to Kirby is how to take Synergetics or, what Kirby's done with this Martian math, human math, how to flip it around and say, well, these are the questions that we're pursuing. This is our research program, because I think that's a fundamental reason why Synergetics is kind of stuck, is that you had this very creative person, but he didn't think in terms of questions. He kind of thought, he gave his example in terms of answers. So I'll give one maybe just point in terms of what John said. If you study Pascal's triangle, and you see that there's like a 1, 3, 3, 1. So a triangle has like 1 face, 3 edges, 3 vertices, and then 1 what? You see, what's this 0-dimensional thing? And so I think Pascal's triangle says that that's the center of the triangle. Exactly what you're saying. That's what you need. Like, and he made a very interesting insight. Like, that's observers. So like, if you go to the next level, in Pascal's triangle, it'd be 1, 4, 6, 4, 1. Well, that's the tetrahedron. It has 1 volume, 4 faces, 6 edges, 4 points, and then 1 what? I say it's the center. Now, if you take that center and you wiggle it around and you pull it out, see, now you're going to have 1, 5, 10, 10, 5, 1. You're going to have 1 4-dimensional space. You're going to have a 5 tetrahedrons. You see, you're going to have 10 faces, 10 edges, 5 points in one center. See, so with 5 points, you can think in 4 dimensions, like in the real way. You see, you can actually see it, and you can actually think, and you can keep going. You see, so mathematicians would just keep going. They don't see why we stop. But this point that, like this insight to say that center, what I would call, is the observer, and the observer keeps. See, so if we start to think in terms of questions, this thing becomes very powerful. Otherwise, we have the limitations of Buckminster Fuller's mind. He seems to be very limited by these 3-4 dimensions. But my challenge to Kirby is like how to be not limited by this idea of relative truth, but to say, hey, absolute truth, lets us listen to nature, because Pascal's triangle is like not the physical nature, but like mathematical nature. So that's my challenge to Kirby.
Thank you, Andreas. Kirby, would you like to respond? Two parts. One is the point about absolute truth, but and the second one is about questions. Can you identify the core questions behind Synergetics?
Well, I think in the context of what was Fuller trying to do, he was suicidal in 1927, and then he dedicated his life to how can I make the biggest difference in the shortest amount of time? And he didn't know at the time. He had, as a kid, he'd always been kind of a contrarian, as you can see, right? So but he was trying to do something for humanity. And he thought that he had come up with, you could say, a diagnosis. He thought that humanity had suckered for 90 degrees too hard. Like we needed to get more into our 60-degree frame of mind. And maybe we've done that already. Speaking of Pascal's triangle, there's Pascal's tetrahedron also, right? Where you have one ball at the top and then 3 under it and so forth. And you basically fill each ball with the number of routes that go to that ball. That's the same for Pascal's triangle. You can see the numbers in Pascal's triangle as the number of individual ways that you can bounce down to that number. There's 20 ways to the 20, but only one way to the far left. You just have to go left, 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 all the way down. There's only one way to get there. 6 ways to get here, 15 ways there, stuff like that. So I love Pascal's triangle. I call it a grand central station. It's a hub, and I picture it on a giant geodesic sphere as like a station with all these lines coming in and going out. I think in terms of planets a lot, metaphorically, like little prints. Anytime I walk into a namespace or a domain, it's a whole planet because it connects around. Everything connects around to itself. And this is how Fuller wanted us to think, that when you get to complexity and systems, try to connect around. So all of his graphs, what we call in graph theory, we always draw these flat things, but his graphs were always polyhedral. They always connect around in all circumferential directions is how he would put it. How about I just get to the very end of the slides because we're only 3 away.
Okay, let's do that. And then folks, for everybody, I have this question. Because we at 52 Living Ideas also think that questions are fundamental. They're far more important than answers. So my question for anybody who wants to answer it is, what are the core questions that Buckminster Fuller was trying to answer throughout his life? What are the core questions that he asked himself and went on to answer? Okay, so that's what I will ask after the slides. Go ahead, Kirby.
I'm looking at the comments. Julie is looking kind of lost in there with all of this, like what's going on here, which I can appreciate. I like to go to Zooms where I don't really understand half of what's being talked about. So sometimes that works for me, sometimes not. But okay, so this book on the right, this is a book cover. Linda Dalrymple Henderson. She's an art historian, and this is a newer edition of the book than I actually own, so I don't recognize this cover. But it's about the 4th dimension and non-Euclidean geometry in modern art, and she traces all the memes. In other words, you go back to like early 1900s, you've got Uspensky, partner of Gurdjieff, right? He wrote a book called Fourth Dimensional Man or something like this. And when Fuller wrote one of his very first manifestos called 4D Time Lock, which is all about habitat. He's all about habitat for humanity. Fuller wants to house, clothe, feed everyone in the soonest possible time. And he thinks technologically, metaphysically, we're there. We could do it tomorrow. But reflex conditioning, all of our training and background, our sort of knee-jerk thinking, comes from thousands of years of scarcity and insufficiency. So whereas we could copy all the world's music for everyone to have on a thumb drive, that violates copyright, right? It's like giving the wealth away. We have to create scarcity to survive. We don't know how to do any other thing. So we're our own worst enemy is kind of the drama. So he's trying to fight this fight where we overcome our reflex conditioning because we could have a good life, but we don't do it because reflex conditioning. And so Synergetics is his way of trying to open our mind, pry open our minds. And he's got this whole dynamic of mind versus brain. If you read No More Secondhand God, other books you're going to be reading, the mind is like trying to make us, we're trying to get more up to date. It's very, very theological in a way, God, God's grace, and so on. But he doesn't use those words. He does, he talks about God, but mind and brain, stuff like that. So how quixotic is it to go into Synergetics? And I just picked this fun cartoon from XKCD, which shows these folks saying these windmills are kind of ominous looking, and mainly because they look like the tripods in War of the Worlds. The H.G. Wells Time Machine, or H.G. Wells, he wrote The Time Machine, but he also wrote War of the Worlds, where we're attacked by these Martians. And here it's the windmills that look like Martians. And there's Don Quixote ready to defend us against these windmills and so forth. And given I'm into this Martian stuff, I'm saying we're the windmills. In other words, I don't feel like it's a matter of me against the world, the establishment is crushing me and like this. I feel more like Synergetics is what's coming over the horizon. In other words, this is the new, I hate to say establishment, but here's the new way. In other words, I feel like we've kind of won. At least that's what I want to get to when I do these slides. Let's say maybe I fail sometimes. I want to give the impression when I get to the end of my slideshow that this is not something struggling to become accepted, but it is the new status quo. We have achieved world domination, as we say, just in a joking way, in the open source community. That's what we talk about sometimes, and it's obviously conspiracy theories and all this kind of stuff. We kind of make fun of that. So that's E.J. Applewhite. When he visited me, he thought some of my papers were kind of quirky, so he wrote quirky papers on a lot of what I sent him and gave me the option to take them back and not have them go to the Stanford archives. And I allowed some of them to go to the Stanford archives. Jay Baldwin, good friend. Another one you could pick up if you're going into Bucky literature, he wrote Bucky Works, and he's very hands-on kind of engineering. He was a Whole Earth catalog guy, one of them, right? Like the one that's better known, Stuart Brand. He's a friend of Stuart Brand's, like that. And that's the end of my show. So thank you for touring and so forth. Wonderful.
Kirby, that was fantastic. Thank you very much. If you could stop sharing the screen.
Okay, sure.
So folks, I now ask you for two things. One is any answer you have to the question, what are the big questions that Bucky asks and answers? What are Bucky's big questions? Okay, that's first. And second, what did you think about this great presentation by Kirby? So you can talk about both of them. You can talk about one of them, anything that you want. Go ahead and type exclamation mark or raise your hand in Zoom in order to talk only about these two things at this point. And then if you have time, we can do more. Richard, followed by Joe. Richard. Oh, just a second. Let me make sure everybody can unmute themselves. Sorry about that, Richard. Go ahead.
Okay, thank you. I've been interested in that for some time. And in my search of Bucky's literature and work, I came up with two questions that I think he was asking. And I think he thought that he found some answers. But the one question was, do humans in this universe or on this earth have a function? And what is it? Secondly, he was asking the question of, in terms of nature, saying, what is nature's minimum coordinate system? So those are two questions that I read in his literature that he posed. And then he searched for the answers and he came up with his answers. But this part is just on the questions. So these are what I think are two of his questions.
Wonderful.
4 questions.
Wonderful. Beautifully put. Thank you. Thank you, Richard. Next up is Joe, followed by Chad. Joe.
Can I ask actually just a really quick question about the presentation? Or no?
Sure.
It was just,
Okay, we can come to it. We'll have time.
All right, we'll come back to it. So no, I thought it was an amazing presentation. It was mind blowing, and I very much appreciate Kirby's time.
You know what, Joe? There aren't that many people who have typed exclamation mark. So please go ahead and ask the question.
Okay, I mean, I was just really curious as to know what Alexander Graham Bell was actually doing with the tetrahedron back in the day, because that's something that it's just interesting to me to have the historical context of how other people would actually use a tetrahedron.
He called it a kite and he flew them in the air, but he also made towers using the same octet truss system. In architecture, it's called the octet truss, that space frame, and Bucky had a patent on it for a while, but Bell was doing stuff with it long before. I guess didn't try to patent it or anything.
Yeah, that's what I was wondering, if Bell Labs had actually subsequently done anything.
He was flying airplanes.
Okay.
Right.
If you date it, you might find that he was ahead of the Wright brothers.
Very interesting.
All right. So go ahead, folks. What are the big questions that Bucky asks? And what did you think about Kirby's presentation? Next up is going to be Chad.
Well, thank you, Kirby. That was a great presentation. I think Bucky was after a model of the universe. And you look at the tetrahedron and you break it down, and what he really says in the book about the vectors, which are the lines of the tetrahedron, and then the vertex, which is the knots. So you have these strings that are in tension, that are being knotted at each vertex, not even coming in contact with each other, and then the faces, and how that translates to a model of the universe. And you see there's a Nobel Prize this past year on quantum entanglement and how that all relates. And I'm also reminded of, I don't know if anyone's ever made this reference, but to Michael Crichton in his book Timeline, and how he spoke about quantum foam and the foam model, and how that relates to synergetics as well. So I think there's a lot going on there that could be applicable to theoretical physics that's not really being addressed.
Thank you. Thank you, Chad. Next up is going to be Dave, Maritza, and Joe. Dave, what did you think?
Shrikant and Kirby. Yeah, to me, the strength of Buckminster Fuller was, let's look at things differently. Before I was talking about the triangle as the strongest figure, and we were stuck with squares and rectangles. And so that's how I came up with the geodesic dome, which spans an open space with a very light structure. And the other thing I'd mention that very few people, I think, have even heard of it, the Dymaxion car. I think there's a different word for it, but put the drive wheels in front and the steering in back completely upside down from previous thinking. And I think there was so many things he did, said, let's look at things completely differently. And, the the geodesic dome, what maybe he didn't invent, but he popularized, just a wonderful thing for humanity. Thank you.
Thank you, Dave. Next up is going to be Maritza, followed by Joe. Maritza.
I think Bucky asks us to see how we can be more in line with nature. I think ultimately in so many of the things he's looking into, that's what I hear. Like, what I've seen is that it seemed he had a vast respect for the efficiency found in nature. And so he made it his lifelong goal to seek how we can be more efficient and do it with nature in tandem.
Wonderful. Thank you. Joe.
I mean, I think Bucky's fundamental concepts are quite simple. He wants to move us towards utopia. And so he asked all the questions that were based around that. That's what geared all his thoughts. He asked questions about the universe. He would ask questions about why how nature works, but then he would also ask why are economic systems set up the way they are. Why are things like in the operating manual for Spaceship Earth is a perfect example where he talks about the idea of desalinization. Is it really that expensive when you really look at the whole, when you really analyze the whole? So I think he really was a whole systems thinker, but he was actually doing it with the goal of actually for the betterment of humanity and the world itself. So he was able to do that both through, looking through things geometrically, but he was also able to integrate philosophy to that. So he really wanted to know, how does man function in the universe? That's one of the main questions, I think. And then what is it really? How does it function within the universe? And then how does it function within nature? How does man function within nature? And I think that those are profound questions because it moves towards an ideal state.
Wonderful. Thank you. Thank you, Joe. Next up is Becky.
I really enjoyed the presentation. It was very crisp, clear, and presented well. What I also enjoyed was the nostalgia back to high school mathematics and being able to, I guess, appreciate things that were kind of taught rather dryly and simplistically. But in this presentation, it was just conjuring back like all that and saying, no, there's so much depth and richness here. And you can see that tied back to truths within the universe. Simple things like just calculating the volume of the tetrahedron inside a cube, or the mention of the Pascal triangle, which the high schoolers learn as like coefficients for like polynomials, and it's just so much. I think that the presentation was just done so well. So thank you.
Yes, absolutely. Thank you. Next up is Maritza. Maritza, go ahead.
I just listened to Becky. I realized I hadn't made any commentary on the presentation itself. And I have to say, I thought it was great. I really liked how approachable it was. I was a little bit concerned that a deep dive into synergetics would have left me lost, perhaps. But I think, Kirby, you did a fantastic job of feeding it to us in bite-sized chunks and with so many details and explanations that you didn't lose me. And I think that even if someone may have gotten lost along the way, you've provided so many references where we can go and do on our own deeper dive into something you gave us, that I think that that's super helpful. So I have to say this was just a brilliant discussion, a great presentation, and just the manner in which you presented it to us was super approachable. So I just wanted to thank you for that.
Thank you, Marisa. Couldn't agree more. Thank you. Next up is John.
Yeah, Kirby, thank you, particularly for putting those references up before your talk. I thought that was really helpful. So I find the same thing with Bucky. If I read it once, I really miss most of it. But so reading your stuff first, I got a sense, I started to get pretty excited about hearing you, and then seeing the same thing again made so much more sense. So that was very good pedagogy. Thank you.
Wonderful. Thank you. Thank you, John. So Kirby, I thought this presentation was amazing. I was a little bit scared because you're taking on all of Synergetics, and you're going to, and on the top of that, you're going to say, we're going to do a deep dive into it. I said, okay, I don't know how this is going to work out, because, you know, at 52 Living Ideas, one thing that we try to do is to make sure that everything is accessible to everybody. And so I was really scared. I said, okay, how are we going to do this? Firstly, I loved your slides. Okay, when I went through them, I just loved your slides. But I was concerned that how are you going to make it accessible? And I thought just the way in which you broke them up, first giving an overview of what the issues are, then slowly going into mathematics, but going into the mathematics in a very graded way. And I thought you made the points very clear. So I thought it was an exceptional presentation. And I certainly think that, you know, it's accessible to anybody who wants to understand the core of Synergetics. So really appreciate that. On the second question about the questions of Bucky, I think for me, it is stunning. I'm new to Bucky. You know, when he has this experience at 32, I think, where he says that, you know, everything everybody has been telling me, there is something terribly wrong with it. So I am going to try to figure out the principles behind nature on my own, based only on my experience and intuitions and thinking. And so asking that question itself, it is so profound. Almost nobody does that. So that is one. So this independent mind trying to understand nature from scratch, from experience itself. That's one. The second is, what minimum systems can you build in order to make, you know, tremendous positive impact on everybody in the world? What are the minimum systems? You know, thinking in terms of the most effective, the simplest, the minimum systems to produce maximum impact for everybody. Those are the two big questions that I see. But and that's why I'm very excited about this entire series, because those are profound questions. I mean, regardless of Bucky, to the extent to which you ask those questions to yourself, I think you know, fundamental things can happen. So Kirby, do you have any comments about the great questions in Bucky? And what did you think of this guy Kirby's presentation?
Yeah, I was really looking forward to this, and I'm so glad to have this privilege, because I know you guys have been through so many topics, and that's in the spirit of CJ, the comprehensivism that characterizes these meetups, that you're covering so many topics and jumping back and forth between Dante and T.S. Eliot and Confucius and Taoism and Gospel of John. And I think that's perfect. And I like the way the Bucky stuff, as I've been watching it from the sidelines, has just been merging with your natural train of thought. You've got the 4-color schemas already. And I loved Daniel's William Blake. Like, that's a slideshow I could never just jump in and do. I have to think, what would it take for me to be able to deliver Daniel's slides? I'd have to learn a lot more about William Blake. Along those lines, I want to mention, I just found out yesterday that William Blake knew Thomas Paine. I just went through a long documentary about Thomas Paine's life, stuff like that. I like connecting the dots. I like, this author, that author, and by disseminating it through this very literate, culturally aware crowd, I feel like you're going to find connections that I'd never thought of, and that the world is going to have the ripple effects of what we're doing here. This is a good thing for people to watch on YouTube, so I'm glad you're recording this.
Wonderful. Thank you. And Kirby, it is an honor to have you here. I think everybody has the potential of learning so much from you. There are so many people who have been doing such great work on Bucky.
Right. And you're helping me very much in all of this. I want to say it's not like all the Bucky people are talking to each other. It's like you're helping us. Like I had never seen Tom Miller's place or gone into, I've seen him on YouTube. So when you went and did all those interviews with Tom Miller and look around and all his compartments and cubby holes and everything, it's like, wow, I never knew that. And when you had D.W. Jacobs and Peter Meissen on the same call, talking to each other and talking about CJ, then it turns out that was a big revelation for me too. So it's like, I know these people, and yet when I see it all filtered through 52 Living Ideas and Greater Thinking Society, it's like Philadelphia and all that, it's like, it comes back to me much more magnified and organic in a way.
Well, thank you. I mean, see, that's what we try to do for all our meetups, because we have in each meetup, like for example, when we did meetup on Bhagavad Gita, we had this guy Yogeshwar, who was just incredibly deep thinker, who had taken in, he actually recites Bhagavad Gita in his sleep, I think, and has read all the Sanskrit, but he too got a lot of value from talking and listening to the questions, going back and forth. And what happens is that this idea of communication is a very fundamental idea. And Bucky was very big on this. Like the way he talked to people, you see, like almost everybody who has actually ran into Bucky always says, I was there and he spoke for 12 hours. He spoke for 14 hours. Okay, but what does that mean? What does that mean? He thinks that communication with each other has a tremendous life-giving value, because the synergy of such communication is awesome, because it is not just, and it is evidenced by the fact that people still remember those 12 hours, 14 hours as a big event in their lives. Okay, so having all the people who are into Bucky talking to each other, listening to each other, building on ideas of each other, because I mean, CJ was wonderful. I mean, he came up with that idea of 4 on-ramps. I mean, it's such a profound idea of saying that each person has their strengths, but all these 4 things build on each other. So if you can pick up something from Tom Miller, if you can pick up something from John Brett or somebody else, or somebody picks up something like Struppi picks up something from you, all of that is going to add to the richness for all of us. So and many of us, like me, we are just starting out, so our understanding is not as extensive as many of the other people here. But again, the approach is that it doesn't matter what your understanding, what your level is. You try your best, and what happens is that each person has his own strengths, so you make the connections that you can as best as you can, and you proceed from there. So Kirby, really appreciate your comments, because that's the whole purpose of doing this entire thing,
I
this
want to
was
encourage everyone to be in touch. I did put my email in the chat. If you go and save the chat,
wonderful. And let's go ahead and put the email one more time so
Okay.
that people can copy it right away. And folks, this has been amazing. Let me tell you about the next meetups coming up. Give me just a second here. So what we're going to do next is Kurt McNamara is going to be here on February 5th, and he will be talking about Bucky's comprehensivity. He's writing a book on Bucky's comprehensivity. So he's going to be talking about that book. Next is going to be Christopher Zellow. He's, he's a film guy, and he's going to be sharing some cinematic footage of Bucky. Next is going to be Doug Jacobs. I am really looking forward to that one. He's chosen to talk about dramaturgical synergies, so application of synergy in drama. Next is going to be Robert Sandusky. He's a colleague of Harold Nelson, and he's going to be talking about Bucky's design science and the 4 on-ramps. Then we're going to have a session which I'm calling Bucky Lightning Talks, where anybody and everybody is welcome to speak for 5 minutes on any idea of Bucky or any idea connected with Bucky that they find interesting that they would like to share. It does not matter. I invite people who are really, really deep into Bucky and people who are just starting out to share at this point, because speaking is the best way of learning. This is not a passive process. The more you speak, the more you learn. Next is going to be Rupali Sharma, and she's going to be talking about the education philosophies of Bucky and Maria Montessori, comparing them. And then it's going to be Richard Ramsey talking about social tensegrity. And I'll be scheduling a whole bunch of things more. If any of you want to do more, speak more, just get in touch with me. I'm always looking to accelerate this as much as possible. And thank you so much. And Kirby, this was just great. Really appreciate that. Thank you, everybody. Really appreciate you coming here. Always grateful for all the great comments and questions. Bye, everybody.